Alright, we're going to start this unit on stoichiometry with a little history. First off, in 1961, it was determined that we needed some way in order to standardize the mass of different elements and their subsequent atoms. And therefore, we determined that since carbon-12 is such an abundant element and isotope on our planet, that we would give it exactly a mass of 12. And since this was a new unit, we got to make up our own units. We called it the atomic mass unit. And it's the basis by which we obtain the mass for all elements. So carbon-12 is given the atomic mass of exactly 12 AMUs, which stands for atomic mass unit. Now, if you look at the periodic table, you'll notice that in each elemental box, or elemental tile, that within each tile you are given the atomic number, which denotes the number of protons in that element, which gives it its identity, and its average atomic mass. This is a decimal point. Since protons have a mass of 1 AMU and neutrons have a mass of 1 AMU, how is it possible that the average is a decimal point? Well, that's what we're going to calculate today. These masses aren't just made up. We actually use a device called a mass spectrometer in order to obtain the relative abundances of different isotopes. The way that a mass spectrometer works is that a sample is placed within a tube and then shot through this heating device, which breaks the sample up into its components, which are given a positive charge by this electron beam. As they're shot through the tube, magnets attract and repel them. The heavier the isotope, the less it is attracted and therefore bent by the magnets. The lighter the element, my apologies, the more massive, the larger the ion, the more it is pulled by the magnets. The lighter the ion, the less it is pulled by the magnets. As I said, average atomic masses are the average of all the isotopes of a certain element. And we calculate these using the percent abundance. So the percentage of atoms in a pure sample of a substance. The percentage, or the percent abundance, is the number of atoms of a given isotope within the sample divided by the total number of atoms of all isotopes of that element. Data from the mass spectrometer typically comes out as these peaks, where the area under the spike, or area under the peak, relates to the relative number of atoms of that particular isotope. So the mass of the isotope is given below. The area under the peak can be used to determine the relative number of atoms, and in a percentage form. 91% of the time, this sample of neon was neon 20. 0.3% of the time it was neon 21, and 9% of the time it was neon 22. Now, to determine the average atomic mass, it's a weighted average based on these percent abundances. So it's much like your weighted GPA. So the way that we're going to calculate this is we're going to take the percent abundance and multiply it by the mass of the isotope, add it to the same thing for the other two isotopes, or however many isotopes you have, total it up, and that will give us the average atomic mass of, in this case, will be neon. So I'll start with neon 20. 91% of the time, neon 20, or 91% of the time, neon was neon 20. So 91% of the time we had neon 20. However, we aren't going to use this percent as a percent. Instead, we've got to change it to a decimal form. So the decimal place is here. If we move it once, that would be dividing by 10. Move it twice, we're dividing by 100, so that we're going back to the decimal that it was. So 91% translates down to 0.91. We're going to multiply that by 20, which will give us, oh, my calculator seems to shut itself off. .91 times 20 is going to give us a fractal abundance of 18.2, or fractal mass of 18.2, because this is a smaller part of the overall mass of neon. This is just that of what is given to it, given to its average by neon 20. So now let's move on to neon 21. 0.3% of the time, neon was neon 21. Again, we cannot use it as a percentage. That doesn't do us any good, so we're going to move the decimal point. We move it once, that's dividing by 10. Move it another time, that's dividing by 100. We're going to multiply these two together. 0.003 times 21. We end up with 0.06. Lastly, neon 22. Neon 22, 9% of the time, neon 9% of the time is neon 22. We again are not going to use it as its percentage. We're going to divide by 100, so move the decimal place twice, and for the sake of time, I'm just going to do that now really fast. When we multiply those two together, we get, wait for my painfully slow calculations, 1.98. Now if we add up all of these numbers, we'll end up with the average atomic mass of neon. So we're going to add these up. We get 1.98 plus 0.063 plus 18.2. And voila, we've got the average atomic mass of neon, 20.243 AMUs. Since the mass is a definite counting number, 1 proton, 2 protons, 3 protons, 20 protons, to give us neon, it has an infinite number of sig figs. Therefore, we have no sig figs here to base our answer on. So we're going to take this out. The AP test requires 3 sig figs. Since we only added 3 sig figs, would be 3 places after the decimal point here. So we'll just leave this as 20.24. Put that as your answer, circle it for your grader, and we are good to go. Now you know how to calculate average atomic mass.